Local large language model infrastructure is the hardware, runtime software, storage, interfaces, controls, and operating practices used to run model inference on systems you control. The model may live on a laptop, workstation, gaming PC, mini PC, server, or managed private environment. Local inference sends prompts to a model running in that environment. A cloud API sends requests to an external provider under its service, security, pricing, and data handling model. Hybrid designs may route different workloads according to sensitivity, quality, cost, or availability. Hardware choices include CPUs, discrete GPUs, unified memory systems such as Apple Silicon, system memory, storage, networking, power, and cooling. Software choices include model formats, runtimes, drivers, user interfaces, local APIs, monitoring, and access control. Local operation can improve data control, offline capability, experimentation, customization, and cost predictability for steady workloads. It also transfers responsibility for hardware limits, software updates, security, backups, availability, and model governance to the operator. Performance depends on the complete configuration. Model architecture, parameter count, quantization, context length, prompt size, batch behavior, concurrency, runtime, acceleration backend, and cooling can matter as much as the device name. The right question is not whether local is always better. It is whether a measured local system meets the task's quality, privacy, latency, throughput, cost, and operational requirements more effectively than available alternatives. Data control is a common reason for local inference. Prompts and outputs can remain within an approved environment when the application, logs, interfaces, and supporting tools are configured accordingly. Local execution does not automatically prevent leakage. Offline capability can support field work, isolated labs, unreliable connectivity, or continuity needs. The model, runtime, dependencies, documentation, and required reference data must already be available and maintained for offline use to be meaningful. Local systems support experimentation with model families, quantizations, prompts, adapters, and runtimes. Teams can inspect performance and behavior without every request becoming a metered external call, although hardware, electricity, engineering time, and maintenance still have cost. Customization may include retrieval over approved data, structured workflows, domain prompts, fine-tuned or adapted models, and local integrations. Each change creates evaluation, security, provenance, and lifecycle responsibilities. Hosted models may offer stronger capability, larger context, managed scaling, rapid updates, and less infrastructure work. Local models may have lower quality on difficult tasks, limited concurrency, hardware constraints, and slower access to new capabilities. Choose local when its control, latency, offline, integration, or economic benefits match a real requirement. Do not choose it solely to avoid governance or because hardware ownership feels equivalent to privacy. Hybrid approaches are often practical. The CPU handles general computation, application logic, tokenization, and inference when no accelerator is used. CPU inference can be useful for smaller or highly quantized models, but memory bandwidth and core behavior influence performance. A GPU provides parallel compute and high bandwidth memory suited to model operations. VRAM is memory on or available to the graphics processor for waits, caches, activations, and runtime overhead. Insufficient VRAM can force offload, reduce settings, or failure. System RAM holds the operating system, runtime, model data, CPU resident layers, cache, and applications. Unified memory architectures share a memory pool between CPU and GPU, reducing some transfers, but still operating within total capacity and bandwidth limits. Storage capacity and speed affect model downloads, startup, swaps, logs, datasets, and backups. Models can consume many gigabytes, and keeping several formats or quantizations multiplies requirements. Preserve enough free space for safe operation and updates. PCI Express connects discrete devices and can affect transfer behavior when layers or data move between system memory and GPU memory. Power supplies, cooling, chassis airflow, and electrical capacity determine whether peak performance can be sustained safely. Laptops trade portability for thermal and power constraints. Desktops are easier to cool and expand. Consumer hardware may provide strong value, while workstation or server hardware may add memory, reliability, management, and support. Match the platform to workload and operational expectations. Parameter count describes one dimension of model size, but architecture and implementation also matter. More parameters usually require more memory and compute, yet a larger model is not automatically better for every task or runtime. Quantization reduces numerical precision to lower memory use and often improve practical inference speed. Lower precision can affect output quality differently across models and tasks. Test the actual quantization rather than assuming one label guarantees a result. GGUF is a common model file format used by Llama.cpp compatible runtimes. A file name may describe architecture and quantization, but compatibility also depends on runtime support, tokenizer, prompt template, and model metadata. The context window is the number of tokens the system can consider in a request and conversation. Longer context increases memory use, prompt processing time, and the chance of irrelevant information. Advertised maximum context is not a default operating target. During generation, the key value cache stores attention information for context. Cache size grows with model design, context, concurrency, precision, and runtime. A model that fits at startup may run out of memory during longer or simultaneous requests. Fit planning includes weights, cache, runtime overhead, display use, operating system load, and safety margin. When the whole model does not fit on the accelerator, partial GPU offload can place some work on the GPU and some on the CPU. Measure speed and stability under the intended workload. Llama.cpp is a low-level local inference ecosystem that supports compatible model formats and multiple hardware backends. It offers detailed control and can serve as a foundation for command-line tools, applications, and local servers. Llama emphasizes straightforward model management and a local service interface. LM Studio provides a desktop experience for discovering, loading, testing, and serving supported models. Both can simplify common workflows while retaining runtime-specific limits. OpenWebUI provides a browser-based interface that can connect to supported local or remote model services. Text generation WebUI offers a broader experimental interface at a high level. More features also create more dependencies, settings, and security surface. Local APIs allow scripts and applications to call a model service. Compatibility with a familiar API shape can ease integration, but authentication, network binding, request limits, logging, and data exposure still require deliberate configuration. Model management includes source verification, license review, naming, storage, checksums where appropriate, prompt templates, version records, evaluation, and retirement. A model file is a software and supply chain dependency, not just content. Start with the simplest tool that meets the requirement. Validate one model and workflow before adding orchestration, agents, retrieval, multiple users, routing, or distributed services. Complexity should follow measured need. Windows, Linux, and Mac OS can all support local inference. The practical choice depends on hardware support, operator scale, application needs, security controls, automation, and the ability to maintain the environment. NVIDIA acceleration commonly relies on CUDA-compatible drivers and runtimes. AMD's support may use ROCm or other compatible paths, depending on hardware and operating system. Vulkan can provide a cross-platform acceleration option for supported runtimes. Apple Silicon uses Metal and unified memory, allowing CPU and GPU components to share a memory pool. Available capacity, bandwidth, thermals, and model support still set limits. Unified memory should not be treated as unlimited VRAM. Driver and runtime versions must align with the hardware, operating system, inference software, and libraries. A powerful GPU can perform poorly or fail to load a model when the acceleration stack is unsupported or inconsistent. Stability matters more than chasing every update. Maintain a known working configuration, record versions, review release changes, test upgrades, and preserve rollback options. Security updates and unsupported dependencies still need timely attention. The software environment is part of capacity planning. Background applications, display usage, antivirus or security scanning, containers, virtual machines, and multiple runtimes can consume memory and complicate troubleshooting. Standardize before tuning. Tokens per second describes approximate generation speed, while prompt processing speed describes how quickly input context is evaluated. A system can generate quickly yet pause for a long prompt, or process prompts quickly while generating slowly. Batch settings can improve throughput, but increase memory use and may affect latency. Concurrency changes the problem again. Several users or jobs compete for compute, cache, and memory. Benchmark expected simultaneous demand, not only one ideal request. GPU offload moves supported model layers or operations from CPU execution to an accelerator. More offload often improves speed until memory pressure, transfer overhead, or backend limits dominate. The optimum is configuration specific. Context length should match the application. Loading maximum context for short tasks wastes cache and prompt processing time. Retrieval, summarization, code, and chat workloads have different useful context patterns. Memory pressure can cause allocation failures, swapping, severe slowdown, or service instability. Thermal throttling can reduce sustained speed after an impressive short benchmark. Monitor temperatures, clocks, memory, power, latency, errors, and queue depth over time. Benchmark practical workloads with representative prompts, output lengths, context, models, quantizations, concurrency, and acceptance criteria. Record quality as well as speed. The best setup completes real work reliably. It does not merely win a synthetic tokens per second comparison. Local does not automatically mean secure. A model server bound to the wrong network interface, an unauthenticated API, a shared desktop session, or an exposed web interface can make sensitive prompts and compute available to unauthorized users. Apply least privilege, individual accounts, authentication, network segmentation, secure remote access, request limits, and administrative logging according to risk. Do not expose a local inference service directly to untrusted networks. Handle model downloads as supply chain inputs. Use trusted sources, review licenses and provenance, validate expected files where appropriate, scan supporting code, and avoid running unknown installers or model-specific scripts without review. Prompts, retrieved documents, outputs, uploads, caches, chat histories, telemetry, and logs may contain sensitive data. Define collection, access, redaction, retention, backup, and deletion. Disable unnecessary logging rather than assuming it is harmless. Patch the operating system, drivers, runtimes, interfaces, libraries, and integration code through a tested process. Backup configuration, prompts or evaluation assets where required, access controls, and service documentation. Models themselves may be reproducible downloads, but local customizations may not be. Monitor availability, latency, memory errors, queue depth, temperature, disk, failed requests, and unauthorized use. Responsible operation also requires model evaluation, user guidance, escalation for harmful output, and a clear decision about when a cloud or human expert is more appropriate. Local LLM infrastructure is a systems engineering problem. It combines CPU, GPU, VRAM or unified memory, system RAM, storage, power, cooling, operating system, drivers, runtime, model, interfaces, security, and maintenance. Local and cloud inference offer different control, capability, cost, scaling, privacy, and operational trade-offs. Choose according to measured requirements rather than ideology. Model fit depends on parameters, architecture, quantization, context, cache, concurrency, offload, and overhead. A model that loads is not necessarily stable or useful under real demand. Start with a simple supported stack, trusted model source, known configuration, representative benchmark, and clear acceptance criteria. Measure prompt processing, generation, latency, quality, memory, thermals, and failures. Protect APIs, accounts, networks, prompts, documents, logs, backups, and model supply chains. Scale only when a real workload justifies more hardware or orchestration. Strong local systems are maintainable, secure, measured, and appropriately modest.